Greetings, physicists. Last time we talked about series circuits, a circuit with a single path where current passes around and there are voltage drops in between each resistor, all right? And that's how we determine current, and we have a set relationship there. Today, we're gonna talk about a different circuit design, and that is going to be parallel circuits. So this is part of the Unit 4 Electricity and Magnetism Day 1 lesson on parallel circuits. How can we determine the current, voltage, and resistance in parallel circuits, all right? And so before we get into this, I want to use the analogy of a multiple lane highway. Perhaps you've driven on a highway. Perhaps if you haven't, you've ridden in the subway. And so on the subway, the analogy that I would use of parallel circuit is the difference between the local and the express tracks, okay? So the local and the express tracks often go to the same places, all right? Obviously, the express skips some stops, and so you get a faster journey, and I would liken that to current traveling faster with less resistance on that circuit pathway. But the analogy of a parallel circuit, and I'm gonna draw here for a second. Imagine that we're on a highway now, and there's traffic in each one of these blue lanes going this way, all right? And so maybe there are a couple cars on this lane, maybe there are 4 cars in the middle lane, all right? And on the outside lane, the leftmost lane, there's 1 car, all right? So the way that cars behave, or drivers in cars, if they're trying to get someplace quickly, is much like the way that electrons behave in a circuit. And that is that they're going to look for what we call the path of least resistance, all right? I'm gonna write that here. Current finds the path of least resistance. And the reason I'm using that, you might have heard that phrase before, path of least resistance. And usually what they're trying to tell you when they say path of least resistance is to say the easiest way to do something. And so the easiest or most efficient way to do this, that is get from point A to point B, for these cars would not be to stay in the middle lane. And so they might change lanes over to here. One might change a lane over to here, okay, and so on and so forth. And you'll see a reconfiguration. And then let's say that traffic builds up in the leftmost lane, then they might shift over to a different lane. And current in parallel circuits will behave the same way. So we can see here, I'm gonna clear this. Now that we have that analogy that current's gonna find the easiest path, the quickest path for it to flow along, much like taking more than one train that goes to the same destination, we're able to divide up the traffic between the local and the express trains. If we look at this, each one of these circuits receives the same amount of voltage, all right? So picture the idea that each one of these light bulbs is a resistor of a kind. That is because it's resisting current, it is putting it to a different usage, and that usage in this case is powering the light bulb and giving us light, electronic light or electric light, okay? And so it passes through here, but the same amount is going to pass equally through each one of these. So the way that we analogize that is that the voltage drop across each one of these circuits has to be equal, all right? And then we're gonna calculate the current accordingly, all right? The total current is gonna be the sum of all the individual currents passing through each resistor. And if there were greater resistance in, say, the bottom light bulb as opposed to the top light bulb, that would mean that there is less current passing through that bottom light bulb and more current passing through the uppermost light bulb, all right? So the thing that you wanna take away in a parallel circuit, voltage drops are the same as total voltage. And then also in a parallel circuit, total current is equal to the sum of individual current along each path. All right, I'm sorry about the coloring there. I'm going to change this so it pops a little bit more. That's easier to read when I highlight it. And I'm going to change the color. All right, we can see parallel circuits. On parallel circuits, the total current is equal to the sum of the individual currents along each path. All right, so we have two relationships that are already a little bit different. We don't have voltage drops in the same exact way, nor do we have current being calculated in the same way. If you recall, current is not changing, all right, across these different parts. Voltage is changing. We have the flip relationship. In this case, voltage is not changing across all the different circuits in a parallel circuit. However, current is changing and it is added up. And so they use the analogy of a river, all right? And obviously water is going to find the path of least resistance as well. I want to go back to the mathematics now, and I want to talk about Ohm's law, which is that current is equal to voltage divided by resistance. I'm going to write that here as well in red. Current equals voltage divided by resistance. Okay, and so since our current, our total current, is going to be the sum of all of our individual currents, then we can set up a relationship the way they do in the following slide. Look here, I'm going to clear that because it's running into their graphic. We know since the total current is the sum of the individual currents, I'm going to put a text box next to here. And this is something I suggest when you're making your own notes. What you can do is you can open your own Zoom. All right. You can take the slides and you can make notes next to them in order to clarify things. So total current equals sum of individual currents. All right. That's our first note to ourselves. Here we take Ohm's law, and we're replacing I1, I2, and I3 with our relationship in a parallel circuit, which is that total current equals total voltage divided by resistance 1 plus total V divided by resistance 2 plus total V divided by resistance 3, and so on and so forth, okay? And once we set up that relationship, we can eliminate that VT by dividing it on both sides, and we end up with this relationship here. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3 dot, 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 plus 1 over Rn, depending on how many parallel circuits we have set up in this overall parallel circuit board. And so I'm going to use their one slide as an example, and then we're going to go through some examples together, because this is a little bit weird. It's a little different from the way that we calculated with series circuits. So what we're going to do is write down our givens. I always like to do this first. So we're given that R1 is equal to 60 ohms. R2 is equal to 30 ohms. R3 is equal to, let's see, 30 ohms as well, sorry. And they tell us that VT, or the total voltage, is equal to 90 volts. Okay, and so first of all, we can take our individual resistance and we can calculate the equivalent resistance using the formula that we discovered on the previous slide, all right? So that is that 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 over R3, all right? And now I'm going to plug in the actual numbers, and let's see where we get. What you're going to see, very interestingly, is that the equivalent resistance is always going to be less than the individual resistances, all right? Let's see that play out mathematically. So 1 over Req is going to equal 1 over 60 plus 1 over 30 plus 1 over 30. Now that we have that, we can make common denominators, and we can combine all these. So 1 over Req is actually equal to 1 over 60 plus, if I convert 1 over 30 to a base or a denominator 60 fraction, I can say that's 2 over 60, and that's going to be the same for the other 1 over 30. That's 2 over 60 again. Now I can add them all together. Remember, when we add fractions, we add numerators and we keep the denominator the same. We just have to have like denominators. So we have 1 over REQ is equal to 1 plus 1, or sorry, 1 plus 2 plus 2, all divided by 60. In other words, 1 over the equivalent resistance is equal to 5 over 60. And now we can just take this very simple step. If I know that 1 over REQ equals 5 over 60, I can just flip both sides and I can say that REQ over 1, which is just REQ, is equal to 60 over 5. And now I can just divide those two numbers and I can say that the equivalent resistance is 12 ohms. Okay. Now that I have that, I can also calculate the current through each resistor. Now, let's remember that each one of these resistances, like we saw in the previous slide, I'm going to change the color. Each one of these resistances is equal to, so first of all, the total resistance is equal to the individual resistances added up together. But we know that I1 is going to equal the total voltage divided by the resistance on that circuit. Okay, and so I can take my total voltage, which is 90 volts, and I can divide that by the resistance on the first band, which is 60 ohms. And I can say 90 divided by 60 is going to equal 1.5 amperes. All right. If I continue on, I can calculate I2 and I3. They're going to be the same because I have the same level of resistance on each of those. So I2 is going to equal 90 volts divided by 30 ohms. And that's just going to be 3 amperes. And that's the same. I don't even need to calculate it for I3. And now finally, I can go down here and I can calculate IT. It's the same as the 3 individual resistances added together. That's going to be 1.5 plus 3 plus 3, or 7.5 amperes. All right. And so there we have a simple calculation of getting equivalent resistance for a parallel circuit. I wanted to show you that even though the problem does not call for that, the problem just wants you to get the current. Okay, but we went a step farther. We're able to get each individual current. There's I1, I underlined I3, here's I2. All right, we were able to get the total current flowing through this parallel circuit. And down here through this long calculation, I'll label that in a different color, we were able to calculate the equivalent resistance for this circuit. Now, I thought maybe quickly I would do one more just to underline this technique. So we've done everything that you might have to do for calculating voltage, current, resistance in a parallel circuit. Let's do it one more time to reinforce. So I've got a separate worksheet here. Again, we know the voltage of the battery, it's 24 volts. And then also we know the resistance on each lane, if you will, in our parallel circuit. So first of all, we know that our voltage is going to be 24 no matter what lane of the parallel circuit we're on. They're all getting the same amount of voltage, but the resistance is different. All right. And so our I1, that's going to be our V1, which is our VT, divided by our R1. All right. I'm just going to plug in the numbers that I have there. 24 volts. 12 ohms, 24 divided by 12 is 2 amperes, all right? And so I've got 2 amperes for this one. Can you calculate the resistance on R2, well, or on the lane with R2? It's going to be very simple. I2 is going to be VT again, because our voltage drops remain the same throughout. VT divided by R2 is simply going to be our 24-volt battery divided by 24 ohms. And that's going to give us 1 ampere. So our total current, that's going to be I1 plus I2. Use the handwriting here, but I hope you get the picture. That's going to be 1 plus 2 amperes or 3 amperes. All right, so we know our IT is 3 amperes. We know I2 is 1 ampere. And now finally, the equivalent resistance, I'm going to calculate over here in green so it pops. We know again that 1 over REQ is going to equal 1 over R1 plus 1 over R2. So 1 over REQ will equal 1 over 12 plus 1 over 24. I have to convert them to the same denominator, so I can multiply top and bottom of the first fraction by 2. Get 2 over 24 plus 3 over 24 plus 1 over 24. Sorry, I'm getting ahead of myself, because when I add those together, I get 1 over REQ is equal to 3 over 24. And now I flip it. REQ over 1 is the flip of that fraction, and that's just REQ, and that is 24 over 3, and that equals 8 ohms of resistance. So now we've also got our equivalent resistance. I hope these examples were beneficial to you, and as we continue through electricity, I will be right there by your side. See you soon.